Our first speaker is Mark O'Leary, and he's going to talk about some of the roadmaps for Comcast and some ideas here. Mark O'Leary is the Regional Vice President of Business Services for Comcast California Region. Mark has held various executive positions in the telecommunications, cable, software, and network industries. With that, I want to welcome Mark, and if there's going to be an opportunity for questions and answers at the end of Mark's presentation, and Chris, where's Chris? Oh, there's Chris up there. Chris will have a microphone that we want to take to you because we are streaming live, so we want to make sure that folks can hear the questions. So, thank you, Mark.
Thanks, Luis. Good to be here. So my 30 minutes is going to be kind of like a Roger Altman film, you know, where there's like 3 separate different stories, vignettes, because CENIC is, it's engineers, it's educators, it's researchers, so hopefully there'll be something for everybody in it. The first thing that I want to talk about is, over the last 10 years, the cable companies have invested billions upon billions of dollars in kind of extending a residential infrastructure into a commercial infrastructure. So everything from running fiber to buildings and office parks and schools to investing in Metro Ethernet. So we're going to hone in a little bit on Metro Ethernet and why the investment by all of the cable companies, generally known as MSOs within the industry, why are they investing on Metro E? Why did they pick Metro E? Then we're going to do a bit of a lane change. We're going to talk about the digital divide, the fact that there's millions of families in this country that don't have internet access, and a lot of them that don't even have a computer. And an initiative that we're running nationwide, and let's take a look at kind of the how and the why of that. And then along the same theme of public-private partnerships, I'm going to talk about a public-private partnership that we did up in San Mateo, north of here, obviously, in 2011 to provide broadband to a city that really didn't have what I would call competitive broadband through a public-private partnership. So, over the last 10 years, the cable companies have jumped into the commercial business. They started out small. They started out with mom and pops. They basically put racing stripes on their residential products and you know, did 24/7 customer care centers and got out of the gate pretty quickly. In the last 3 years, the heavy investment has been more on the enterprise side of the segment. So generally the people in this room, right? Again, whether it's fiber to the building, whether it's building a robust edge of Metro E on our network, the money right now in cable, because it's so competitive from a video standpoint and there's so many players, it's not growing a heck of a lot across the industry. So if you want to take a look at operating cash flow, if you want to take a look at revenue growth for all the cable companies, commercial is the market. It really is. So why did we, coming down a few clicks, why did not just Comcast, but every cable provider choose Metro E as a standard, as an investment platform? First off, Metro E is, and everybody understands the standards, and you know, we were the first carrier to be CE2 on Metro E, and you know, we're a big part of the MEF, Metro Ethernet Forum. You know, everybody understands kind of the logic of, well, are you really doing is you're extending what the dominant local area network platform is out to the wide area network. Yeah, and on one level that's true. But the other reason that we chose Metro Ethernet, the cable industry, not just Comcast, the other reason we chose it is Metro Ethernet is incredibly scalable and it's non-proprietary. So you can go from 1 megabit up to 10 gigs in logical, you know, in logical fashion, in incremental fashion, because there is a granularity to it. So whether you're in finance or whether you're an engineer, a network engineer, or an end user, that makes a hell of a lot of sense to go with a product, to go with a standard where you can get granularity and scalability. In terms of reliability and security, it's Ethernet, right? And that's part of the MEF, and the carrier portion of MEF's charter is to constantly optimize it. So from a reliability standpoint, a QoS standpoint, a scalability standpoint, the heavy investment by the MSOs has been in Metro Ethernet. I mean, the standard's been picked, and that's, you know, and that's going to only be optimized in the future. Boy, that came out good. I didn't think that would come out too good. So that's pretty readable. So just kind of taking a look at the, you know, the big players, and there's obviously some smaller players, some regional players that also, almost to an MSO, are going with Metro Ethernet as a standard. So along the services line, you can see it's pretty robust. We have ELANs, private lines, EDI, which is internet, point-to-point, VLANs. So it's very robust. And in terms of speeds, like I say, Cox actually goes down to 256 to 1 gigabit. We go from 1 meg to, and this is a little dated because we'll go up to a 10 megs. Again, in very, very granular fashion. Okay. So I brought this out for the engineers in the audience. So if you take a look at, now this is our network, but by the way, I've worked in a past life with Cox's network and know a lot about Time Warner. This is typically how the networks work. And I'm going to kind of bring up an evolutionary point here. How the networks basically work is you have your backbone, okay? Now, what the CRANs are is they're the regional networks. So let's take California as an example. There's no Comcast down in Southern California. It basically runs up Central California and runs from essentially San Martin up through San Jose, Silicon Valley, up to Fort Bragg. But that's a regional network, right? And the regional networks are not linked from a commercial standpoint. So important point that I'll come back to in a second. And it's the same way with the other cable companies. But, you know, kind of an interesting thing is we have fiber nodes, and we have HFC nodes off of these, you know, would be the Northern California network. And when you take a look at kind of aggregately the scale of this, you know, it's pretty impressive. You know, the thing that I kind of point to is 418 terabits of data a month just to the home, not even including commercial services. You know, 91 million emails a day. So that has to be a pretty robust network to provide the type of capability to hit these type of, you know, really scaled numbers. But like Cox, like Time Warner Telecom, their backbone would look fairly similar to this. However, again, although we do have a core backbone, the architecture right now and the services right now are localized. So let me give you a classic example. Right now, there's not a cable company that could go to a Kaiser, who has, you know, hundreds and hundreds of hospitals and medical facilities up and down the West Coast, and give them one network, because again, these regional networks aren't linked. So in terms of trends, by all the cable companies, one of the big trends is up here. It's the on-net access, or excuse me, the off-net access. So what we're doing is very rapidly, because we've done a lot of infrastructure build out in the regions, and now it's time to link the regions using bilateral agreements with each other. So that, again, take a Kaiser, that each of the MSOs could get access through the other MSO in terms of these off-net access. So in terms of trends that you're going to see in the next 3 years, because the last 3 years, the big trend for the cable companies in commercial was Metro E. It was investment in Metro E, and it was also fiber infrastructure build. The next trend is going to be the rapid expansion of off-net access. So we all can expand our footprint, right? And the other thing that you're going to see with all of the MSOs is, if you take a look at a metropolitan area in any city, the cable companies will not have the capability to get to some big Class A buildings, okay? Because you can't go to downtown San Francisco and start ripping up the streets. And also the cost, to a degree, is prohibitive. However, there's a lot of HFC. About 50% in our footprint, about 50% of the commercial buildings have HFC, or coax, as you know it, in the buildings. So the exciting thing for us is we just launched Metro E over HFC. It's starting off at only 6 meg because we're testing to see, especially the upstream activity in our network of it, because it's symmetrical. But this is going to be probably one of the next big things in the cable industry, is running Metro E, not on glass, but on HFC. And in the labs, we run a gig, but then again, the labs is a lot different than real life, right? So this is the next thing to kind of keep an eye on, because what it does is it dramatically expands the MSO or the cable company's footprint. And it also provides low cost because we don't have to trench and lay glass at, $30 a foot. So that's Metro E, and that's kind of trends as to where not just Comcast, but all the cable companies are going. And also what I think, again, is an interesting factoid, that in all cable companies, 50 to 60% of their revenue growth and operating cash flow is now coming from commercial business. So it's been wildly successful as a long-term strategy for all the MSOs. So let me shift gears here into a program that we partnered nationwide with educators in the community called Internet Essentials, that was aimed at increasing digital literacy and also closing the gap between middle-income families and affluent families, our families, right? And families that can't afford the $40 a month or the $20 a month or the $18 a month for broadband access. So here's a quote from Julius Janikowski, who's the FCC chair. And we also worked with the FCC in launching this program. So if you take a look at, and this is the FCC's National Broadband Survey. If you take a look at the barriers to adoption for internet, a lot of it comes down to the price of broadband service and also computer price. If you take a look at income below 130% of the poverty line, 48% don't have broadband access. And everybody in the room understands when a household doesn't have broadband internet access, that it really blunts the development and also the options and the choices of the folks in that family. So what we did, working nationally, is, and I was talking to Luis about this, if a family has a child that is in the free lunch program or reduced lunch program, K through 12, they qualify for this. There's no credit checks. They immediately qualify for this, right? It's $9.95 per month and $146 computer they have the option for. In terms of the success of it, we launched this back about 13 months ago, and we picked up 175,000 households that we're now providing broadband access for. So another slight lane change in terms of community partnerships, and this is the first of its kind that's been done in the cable industry. About 2 years ago, we were approached by San Mateo City Council, the Chamber, the Mayor, and in downtown San Mateo, which ironically is only 8 miles from Sand Hill Road, which is kind of the VC capital, venture capital of the world, they don't have broadband access, okay? There's one provider, and it's basically TDM stuff. So you go from a T1 to a fractional T1 to a T45. Well, there's a lot of software businesses in that area that are bandwidth intensive, where that kind of program financially just doesn't work. And as an running a venture-backed company, kind of relying on TDM, you just don't have the money to do it. Okay. So there was no true, accessible, low-cost broadband access. The commercial property owners and the REITs of the A and the B class buildings, their vacancies were high, and the primary reason the vacancies were high was lack of broadband access. It was amazing. I mean, they did their own study, and it kind of blew our mind. So what they did was they approached multiple different service providers, some CLECs, and us, and we said, yeah, we would definitely be interested if you give us, if we can actually accelerate this with the city manager, because we obviously had to tear up streets. Well, we dropped 3 nodes in downtown, and we put in a ton of fiber and a ton of coax. And of the 898 businesses, from small retailers to some pretty big businesses in San Mateo, we lit up every building. And it took us about 6 or 7 months. And I won't get into exactly what the cost was, but it was north of $1 million, okay? And the outcome now, oh, I'm sorry, folks. One of the other players that I didn't mention was the Edge Community Development Group, which really drove a lot of this with us, okay? So the future state, which was May of last year, we picked up, interestingly enough, because it was kind of a crapshoot for us, but we'd never done anything like this before. So for us to break even, we had to get 20% penetration. We've already gotten 38% penetration. And this is still a relatively new project, and a lot of the folks there are still on 3 to 5 year contracts. So for us, it's been wildly successful. They've actually seen vacancy rates go down, since now when folks are looking to move into San Mateo, they now have broadband access. So this is the first of its kind in the cable industry. And as Ray knows, who's one of the executives in California, as Ray knows, there's 4 other communities that are basically saying, whoa, 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 you did that with San Mateo. Take a look at us. We're in their communities, and this is, on the peninsula and near San Francisco. We're in their downtown. There is only one provider. So we're also taking a look at that, but it's been pretty good business, okay? So kind of closing up here, we talked about Metro Ethernet. We talked about what the driver, the commercials, the driver of operating cash flow growth and revenue for the cable companies, which is a little known fact. We talked about Internet Essentials, and a classic example of a cable company working nationwide with K through 12 educators to make something meaningful happen, and then the unique public-private partnership between Comcast and a community that's kind of in all of our backyards in California. So, any questions? Thanks for the opportunity to talk today and to be part of this.
So I was just curious, with your San Mateo, do you see that relates to some of the national efforts with GigU and US Ignite? I mean, trying to build out into communities. Is Comcast looking at that?
Yes, but I'd like to see a lot more kind of kinetic energy around it. So yes, this was the first, and look, like all businesses, the cable companies have to make money, and the other cable companies looked at this, but I think kind of the point being, if you have a good partnership at the front end of it between all the meaningful players, it also makes incredibly good business sense. Any other questions, folks? Thanks a lot.
Thank you, Mark. That was very interesting. Our second presentation is from Christopher Wilks. Christopher is engineer from UC Santa Cruz, CJ Hub Applications and Data Migration Engineer. Chris is a software engineer specializing in bioinformatics with several years of experience supporting and developing software systems used in computational biology with a current focus in cancer genomics. He played an integral role in the setup of CJ Hub and is active on the ongoing development of the system. With that, Chris. Oh, and a reminder, we will have another opportunity for Q&A at the end of the breakouts.
Thanks, Louis. Hi, folks. I'm Chris Wilks, as Louis introduced me. I'm from the Cancer Genomics Hub, CG Hub at UCSC, and actually this is a co-presentation, or would have been, with Dan Maltbie from ANI Systems, who wasn't able to make it here, but I'm presenting. So I'm presenting the network transfer protocol for genomics data. I'll just give you an overview of where we're going. So I'll give you some context of CG Hub, a little bit on data statistics of downloads, and dig into the specific details of GENETORRENT. So just a reference here for context's sake of where the web has come from. I think most of us are familiar with some of these things, at least FTP, good old FTP, and then Gopher predecessing the current Web 2.0. So basically the web obviously adapted over time, grew, simply wasn't built in a day. Slow start, explosive growth, obviously lots of people using it now, and who knows where it's going, maybe semantic web, some other things. Kind of see an analogy here to what we call the worldwide genome web. We're certainly in the sort of the early stages. We see CG Hub as being in storage, access, and transmission. We've yet to see really distribution and transformation happen in this area, we think. Slow start, definitely. The industry sort of lags, really the IT industry in general. There's not a lot of standards, not a lot of cohesiveness among the research groups. Explosive growth, this can be interpreted a couple ways. One is numbers of people. There's not really that many researchers comparatively to the world in general, but they are distributed and there is more and more interest in genomics. But also in data growth. So we have lots of data in genomics, and genomes just produce lots of bytes, as I'll show in just a moment. So where does CG Hub fit in all of this? So primarily we are tasked with storing the data that comes out of what is called the Cancer Genome Atlas project. It's the National Cancer Institute project, and actually we store other projects' data as well, but that's the primary one. It starts with patients in hospitals getting biopsied, samples of their tumors and also their blood are categorized or ID'd, inventoried, and then sent to sequencing centers around the US and actually Canada. So there's a sequencing center up in Boston, or actually Cambridge, Massachusetts, called the Broad Institute. There's one down in Houston at the Baylor College of Medicine. There's one at UNC in North Carolina, and some other places as well. We don't actually do sequencing for this project at UCSC, although we do have sequencing machines at a small scale. CG Hub takes in data from the sequencing centers, specifically in the form of what is called a binary alignment map file. And what this file has is essentially millions of lines, where each line is essentially a DNA read, a linear order of bases, A, T, C's, and G's. This read is then mapped or aligned to the original human reference, human genome reference, produced roughly around 2001, or a version of it. And then certain qualities of the read for every base are also included. So we have 3 separate points of data for each read, and there's millions of these reads in one file that are uploaded to CG Hub, and there's thousands of files, so it's quite a lot of data. This is all overseen by the National Cancer Institute. One thing that wasn't on that last slide is what do people actually do with this data? So it's one thing to actually store it, and that's what CG Hub does. And we don't do that for our own self-interest. We do it for the downstream researchers who download the data from us as a central location. And this is what they do with it, and I don't expect you to fully understand this slide. But it's essentially, the idea is the sequencing centers, as I just talked about, do the sequencing, and CG Hub sits here in the middle, and they upload the data to us, and then the analysis centers, of which UCSC is also a part of in a different group, download the data, agree upon a set of samples that they're going to do analysis on, and they call mutations. Cancer is a genetic disease. It involves aberrations in the genome, changes both at a small level, certain even single bases are changed, all the way up to parts of chromosomes getting knocked out. They run algorithms to detect these and then produce a list of mutations, which eventually some, after they're validated, will make it into publications and support even further downstream research. So that's essentially what people do with the data. So how big are these files? On average, when we first got our initial data set, about 180 terabytes. Each file, on average, is about 18 to 20 gigabytes. And this is a partial genome. It's not even a whole genome. A whole genome will run you at least 75, starting at 75 gigabytes, and can go up to about 350 or 400 or more gigabytes per file. So it's quite a large data set. On the left, we have generally the data download statistics from the last year or so. The start of CG Hub in January of 2012, roughly, started less than 50 terabytes. This is per week downloads. November, first week in November of 2012, we were around 240 terabytes a week going out. So just kind of put this in context. Mark's presentation, very interesting. And that's, of course, home usage. But that was, I think, roughly translated from the 418 terabits is roughly 50 terabytes a month to home. So just to put that in context, this is going to a relatively small set of researchers. So our total set of users who have accessed the system at least once is about 200. So it's not that many people. But they're obviously downloading quite a bit of data. And I should say, as a caveat, this is initiated downloads. We don't have numbers on actual completed downloads yet. As far as the networking goes, we've looked at our network graphs from our firewalls. We are using our 10 gig connection to CENIC, which is good because it's probably not cheap, but it's also a very good thing to have. We definitely would be constrained if we only had a gigabit out. And we may even have to ramp up to 10 or 20 gigs or 40 maybe in the future. That would be interesting. I know there's plans to roll out to 100 on internet too, and possibly at CENIC as well. I don't think we need that yet, but possibly in the future. On the right side, we have downloads for basically about a year and 4 months, and this is a total set, so about 420,000 files, and that roughly translates into about 6 petabytes. So it's quite a large amount of data. It's roughly 15 times the repository size a few months ago. The repository size is about 440 terabytes, and that pretty much grows every month. It was growing at about 5 terabytes a week incoming. That's sloped out. That sloped down. We think it's going to increase, though, or it's going to come back to that at least at some point. That translates into roughly 33,000 genome sequences. So this kind of shows you this isn't just a research project. It's not just a proof of concept. It's running. It's operational. And we think it's running like a rat in a coffee can. I'm going to switch gears here a little bit and talk about GENETORRENT as a protocol for downloading. So GENETORRENT is built off of BitTorrent. And you may be wondering, BitTorrent and security don't seem to go together. Certainly not what you'd think. Certainly the government doesn't think that. But the way we run GENETORRENT, focusing on security, and I should say, actually, why do we need security in this context? Certainly, there are open access genomes. The 10,000 or the 1,000 Genomes project is open access. Anyone can download their data sets. But for us, because we are pulling data from patients who have signed consent forms, we have to protect much of that data behind firewalls and limit the access to those who are approved access. We want to get as many researchers access as possible, but they do have to go through a process to get that. So security is very important. It's not HIPAA compliant because we don't store patients' names or social security numbers, anything like that. I don't know any of that. But we do have their genomes, and that's important as well. But we also need to have a certain amount of distribution and collaboration, and BitTorrent provides that. The way we use BitTorrent, we do not use the peer-to-peer aspect as such. We actually use it in a client-server context. We lock down the seeding servers. We control all of that. We control the tracker. The data channels are encrypted. And clients only connect to us to download the data directly. They don't connect to anybody else. Now, it's possible, given that there are open access genomes, to extend this model to get a true distribution across clients who are interested in genomes and share among themselves. We haven't pursued that as yet, but it would be an interesting future work project. As far as robustness, we leverage the fact that in BitTorrent, by sort of out of the box, by default, every piece of data is hashed and checked on sending and resent automatically if it was corrupted, if the hash doesn't match. Scalability, leverage the fact that anything can be a server essentially in the BitTorrent model, and that means that we can add servers relatively easily to our pool of initial download servers. So the build out is relatively cheap. BitTorrent in general is a well-vetted internet protocol, used obviously by lots and lots of people around the world for a variety of uses, not all illegitimate. And Facebook, for instance, uses it, or it did use it at one point to distribute updates to their servers quickly using the peer-to-peer aspect. It's certainly in use. This is, I think, at least of peak traffic rates, if not of total traffic. Clearly, Asia is a large user of BitTorrent. It's been fading in the US. These are based on Sandy Vine estimates, probably because of Netflix and other media streaming outlets. So how does GENETORRENT fit in the context of CG Hub? So CG Hub has a variety of user interfacing tools. We have a beta of an actual GUI. We tend to be command line centric coming from Unix. But our clients use a command line CG query to query the database or to submit, using CG submit to submit new data, metadata. We have a metadata web services interface running on Apache. There's also a control plane, which controls the upload and download for GENETORRENT. So a GENETORRENT download will start by contacting our web services interface, and that will initiate by pushing out a torrent file, we call it a GENETORRENT file, to a load balancer. This load balancer then dynamically allocates a certain number of servers or actors in this diagram to serve that file to whatever client is accessing it. Part of the communication, though, has to go through this transactor, which is what we call the tracker, the BitTorrent tracker. The BitTorrent tracker talks to the client talks to the servers, and this sort of triangulation of communication. This makes debugging a bit more difficult since it's not one point-to-point transmission, but it allows us to dynamically associate download servers with clients on the fly, which allows us to also scale that at will, basically. We can add more download servers pretty easily to this, and the load balancer just essentially allocates it to whatever servers it thinks the load is not too great on. It generally turns out into a fairly uniform distribution, at least what I've seen. At the bottom here, we're running off of IBM's general purpose file system. It's highly parallelized, and parallelism is a very important part of how GENETORRENT gets its performance. So here you see the parallelism at the file level. We split up a file into multiple pieces. These pieces are about 4 megabytes per piece. And given the size of our files, we have thousands of pieces. These are spread across the GPFS distributed file system. So you get a parallelism at that end. And actually, I'll just move this forward to show the parallelism more distinctly. So we have multiple nodes in the file system serving pieces of this file. We have multiple servers, like I was talking about the dynamic load balancer, serving the file. We have even parallelism on the firewall level. So we have, at this point, 2 firewalls, but this can be extended out. Each one is sort of having the number of download servers to sort of split up the rates. These are all connected at 10 gig. Go through the internet to the client. Now on the client side, there's also an element of parallelism. The client can control the number of concurrent download processes for a given file. The default is 8. And this is actually sort of recommended to match whatever the client has as far as CPUs on their system, physical CPUs, cores, and then whatever file system that they're writing to. So there's parallelism sort of at least 3, possibly even 4 layers of this architecture. And there's 2 main parameters we can parameterize the system. One is the number of download servers. We can change this fairly easily in the load balancer. Right now it's currently at 4, which is relatively conservative. So for any given download, 4 servers on our end will be serving that download. We have a pool of 13 servers currently, and we can add to that, again, fairly easily. And we do have plans of increasing this, and we're pretty sure that that will raise the download rates of probably most of the clients. Again, on the client side, they can choose how many concurrent processes they run, ranging from 1 to 8, which is the default, to even more. If they have more CPUs, if they have a very robust box with lots of cores, then they could raise the limit if their I/O can handle it. This is the actual more physical layout, system-level view of the CG Hub setup with the storage nodes all connected over a 10 gig network, the storage network essentially, and then the download nodes also connected to the storage network at 10 gig, but connecting to the outbound network at 10 gig as well. So very much 10 gig oriented. We have one 10 gig link going out, not just internet too. CENIC is actually there, and we can go out to commercial providers. And this is all in the San Diego Supercomputing Center, so just up the street, essentially. We manage it from UCSC, and we're also connected to CENIC up there. So how about performance? I've been talking about performance. So what do we actually see? So this is this was a set of tests that we ran, and I should say there's a number of factors here. One is that we're throwing away the bits on the client side, so we're not taking a hit with the I/O on the client side. We are reading the bits off the disk or off the cache on the server side. So that's still part of it. We're modifying the number of child processes, so that's being adjusted across this. And we're also adjusting whether we're running encryption or not. The one thing we're keeping constant is the number of download servers. So we went ahead and allocated for maximum performance the file that we were testing on to all 14 of the servers in the pool. And at this time, we had 14 servers. So the main points to take away from this are that when we adjust the number of concurrent child processes on the client side, it certainly the rate goes up. But then SSL does seem to take a hit. So when we raise it up to 30 concurrent child processes all downloading data, the SSL is clearly making a difference here. When we take it off, we jump up to about 419 megabytes per second. So that's almost getting somewhat close to 4 gigabits, 3 to 4. So it's quite good. This is for one download. And I believe this was a 100 gigabyte file that we were downloading. We didn't run it all the way to the end for every test. It still takes time. And you can see that down here, it's still a respectable speed. It's over 2 gigabits per second, and that's encrypted. It's interesting that the box that this was run on has 12 physical cores. They're Intel Xeons. They have hyperthreading, but hyperthreading doesn't necessarily give you a full 2x speed. It's more like 100 or 120, 130%. So even then, we were able to max the number of processes we ran concurrently to 30, even though we only had 12 physical cores, showing that at least without encryption, GENETORRENT isn't fully maxing the CPUs at all time. So it's a pretty good view that we can really get a lot of bandwidth even out of a limited number of cores. And this is sort of further demonstrated in this graph. This table, which is fairly rough. These are rough numbers, but the idea here is the CPU usage, the sweet spot, is using all the servers on CG Hub side and using 8 children. Now this was limited by this client machine, which only had 8 physical cores. We saw that as we put up more children, so using 12 here, the speed dropped off. Maybe it was just too much for the client, whereas the server stayed at roughly 35%. Whereas on this side, when we have the number of servers, clearly the server is working harder and the client isn't fully utilized. So that seemed to be interesting. Anyone can use GENETORRENT and CG Hub. So if you're interested in any of these things I've been talking about, you can go to this page, even right now, if you have the disk space. And you can actually even throw away the bits if you want, just to do speed tests. And you can actually, if you want to save them, we have 320 open access. So these are actual real cancer genome files that are from immortalized cell lines that are no longer protected. And these can be downloaded by anybody. If you're interested, check out this page, send us any questions, or we'd just love to hear from you. Support. These acknowledgements. A lot of people have been involved in this project at UCSC. Our PI, David Hauser, is definitely a visionary in cancer research. Dan Maltbie, my co-presenter who wasn't here today, he may be here tomorrow, but they've done a lot of work for this project. They use we use their ANI Systems Genome Network Operating System, primarily in CG Hub. And then we are run by SAICF as a subcontract to the NCI for this project. If you have any questions, feel free to email me or Dan if you're interested in the software. Thank you for your attentiveness. Any questions? Yeah. So, can you repeat the question?
Oh, sorry. Hi, I just want to know, where are you terminating your SSL? On the servers or on the load balancer in front of them?
The SSL goes directly to the servers themselves. So we basically punch holes in the firewall on our end for access directly to those ports.
Fair enough. Thanks.
Mm-hmm. Anybody else? Great. Thank you.
Thank you, Chris. So I do have a question for you. So currently you're storing everything in-house. Are you looking at other technologies like cloud or something like that to house the data, or because of your privacy?
Right. So security is an important aspect of this. We're not necessarily, we don't have to be HIPAA compliant, but we do have to be FISMA compliant, which is I think it's the Federal Information Management Services Act, something like that. And so there is a certain amount of requirement, like I was talking about, for encrypted data storage. And as far as we know, that the clouds are working on it, but that aspect is who actually has access to the data when it's in the cloud, and then also possibly the costs of putting it in the cloud at this point. It's a lot of data, as you guys can tell, and it's a lot of data that we're storing and a lot of data that's going to be outbound. And if we paid the normal prices, that could be pretty costly. So at this point, we went with our own managed solution here at the Supercomputing Center, which is very reasonable.
And how often do you have to scale your storage systems? It seems like data growth is pretty significant.
It is, actually, and that's a very relevant question. We just scaled it. We were just adding more arrays a couple weeks ago. So I think another petabyte, I believe. Really, the ceiling for this project is 5 petabytes. We didn't buy all the storage up front because that wouldn't have been a good, efficient use of funds. But that's the idea. And then we may get more data than that, and we're looking at compression algorithms and ways of getting more space out of what we have. So.
And I know that Dan didn't make it, but could you perhaps talk a little more specific about their role of NI
Sure.
systems?
So NI built like I said, the Genomic Network Operating System, which is essentially what CG Hub runs on. They also built GENETORRENT. GENETORRENT itself is open source. You can go to our site and download it. And we set that up in CG Hub and worked very closely with them in really the initial alpha and beta versions of the system. And I know the internals of the system pretty well as well. So that was their role. And they continue to support us. We have a contract with them, and they give us software updates. And they actually have their own setup in Amazon currently. You can download the 1,000 Genomes project, which is the open data from their services, I believe, in Amazon. I haven't actually done it myself, so I don't know the specific details. But hopefully Dan will be around tomorrow, or you can send him an email if you're interested.
Right, Chris. And so if anybody's interested in downloading this genome data, do they contact you, or how does that happen?
Yeah, I will. I will send the. I haven't sent my slides to the presenters, the organizers yet, but I will, and I presume those will be made available for download. The URL is in there, or you can email me at cwilks@soe.ucsc.edu, as I put up there. So.
Okay, sounds great. Any other more questions for Chris? No? Oh, just so timely. So our presenter just came in, our third presenter. Azher, you want to come over? So our third and last presentation is enabling scientific discoveries with the LHC data distribution over 100 gig networks. And our presenter is Azher Mughal from Caltech. Azher is network engineer in Caltech High Energy Physics Department. Group is working with CMS Tier 2 Center in Caltech, LHCON, US LHCnet network for providing high-speed network for the LHC community. And I want to thank Azher. Azher, I think, has been multitasking this morning, so he just came from the theater on his other presentations. So with that, I want to thank Azher and invite him to do his presentation. I'm sorry? My presentation was at 10? Well, they finished the work. Oh, okay. So.
Hello everyone, my name is Azher. I'm from Caltech and also wear the hat for the USLC Net. Thanks for being here. Okay, so the talk is today is about the LHC data distribution over the 100 gig networks and some of the experiments that we have done during the SE12 last year. A brief agenda, the motivation behind the 100 gig networks, our experiments during the supercomputing 2012, the network architecture that we deployed over there, the storage design, why we do that, the results, and if someone would like to design a similar kind of kit, then what kind of components they need, and if at the end questions, if any. So the motivation for us is the LHC. We are a group. Our group is basically mostly involved in the CMS physics for the LHC experiments, which are running in Geneva. LHC, CMS, and Atlas are two main experiments. So the LHC experiments with their distributed computing models and global program of LHC physics has a renewed focus on networks with more where the experiments are now running at more high luminosity, and when the experiment will again start in 2015 time frame, then the networks should be ready to capture and to handle that volume of traffic. According to the ESNet, the data volume that will be traveling on over the ESNet, it will be around 100 petabytes per month, which is about 10 times in usage over the last 47 months. Since we are involved in the USLC Net, so right now, when we started about 25 years ago, it is starting from LEP3 net in 1985. It is about 6 million times as what it is today. As it was what it was back in 1985. So CMS and Atlas are generating large data sets which need to be efficiently transferred to end sites anywhere in the world, especially to the tier 1 sites, tier 2 sites, and now the tier 3, which are basically part of the tier 2 through the campus. The networks should have a sustained ability to use ever larger continental and transoceanic networks effectively with high throughput transfers. HEP as a driver of R&D and mission-oriented networks, and at the same time we do the testing for the latest on the current and the next gen networks. So this is a small cartoon that was designed and developed back in 1999 that shows the data hierarchy flows starting from tier 0, which is at CERN, and then tier 1, which is at national level in various countries. For example, in US, Fermilabs is for CMS experiments, while Brookhaven National Lab is for the Atlas. And it shows the tier 1s, the data coming from the tier 0 and then flowing down to different tier 1 centers at 10 to 40, and then following to 100 gigabit per second, then tier 2 centers where UCSC and Caltech are some of the tier 2 centers in US. And now the concept of the tier 2, which has been evolved in the last few years, which are connected to the campus-based tier 2 centers. So there's tens of petabytes per year data which was transferred over the last few years. Since our group is mostly involved in the CMS, so this slide shows you an increase of about 45% traffic volume since 2011. This is a plot for the 2012 only. But if you look back on the 2011 plot, you will see definitely a 45% increase in the volume. And of course, this relates how the experiments are going at CERN. And you also, when you see the wide area network plots of the traffic coming from CERN to US, you'll see about the peaks of 20 gigabit per second. This is a plot explaining about the Atlas. CMS is more compute oriented, Atlas is more network oriented. Here you can see in 2012 peaks of 102 gigabit per second traffic flowing from among the Atlas sites, with different peaks at different during the different conferences, and when the researchers, experimenters basically do the data mining and perform their tests on the data sets. Now a little talk about our 100 gig testbed that we deployed during supercomputing 2012 with the support of various research and educational network providers, especially Internet 2 and equipment vendors like Ciena. So this was basically Salt Lake City, where the supercomputing took place, and this is our booths, the Caltech booth. That just shows some part of the components. I'll show later on the other parts, but this is a Venn diagram that shows the Internet 2 backbone. This is the 100 gig going to University of Victoria, Canada. This is the third 100 gig coming to Pasadena, California. So there were 300 gig links that were established during this conference. So one was going on the south side, one was going on the west side, and one was going on the east side to University of Michigan. And supercomputing venues are provide our group basically a time when we can work on the current generation and the next generation networks, which are still not available to the public, but they are still in the labs, and the people in the future can get benefit from those. So I call it like a mini SciNet rack, where you have couple of routers, switches, special super microservers with few on I/O, disk storage cards, 410, 40 gig, all 40 gig switch, other super micros loaded with the SSD drives. This is a whole rack from DDN and their controllers. These are some of the other object controllers with InfiniBand fabric. And here's a little explanation of what is where. So this whole setup was either 100 gig on the WAN side or either 40 gig within our booth. So there was no 10 gig that was used for the 100 gig demonstrations. We use mainly the super microservers because you can custom design those boxes per your needs. You have options to choose the number of slots that you want to have in that box. Either it is Gen 2 PCI or it is a PCI Gen 3. Either it is an X8 or either you need a X16 kind of slot. But you need to beware while choosing those motherboards, because some slots are mechanical X8, but internally they are X4, or it could be Gen 2. So this is the Alcatel where we terminated 3 of our 100 gig links, and Juniper, we also use Juniper, but we had some trouble with Juniper during the show. These are all the SSD super micro box with new Vertex 4 drives. This is the DDN. This is how it looks like, with 410 in the middle, connecting all the 40 gig boxes and providing the backend to the DDN as a luster back. So on the right bottom, you'll see a PadTech. It's a new name, might be for you. It's a company. It's an optical company based in Brazil, which brought their first OTU-based 100 gig MUX. So we placed a MUX in our booth and a MUX in the Vanderbilt booth, about like 100 feet away. we had a couple of servers in Vanderbilt booth, and we have some servers connected to the PATech 100 gig in our booth. That device was not able to do 40 gig. There were 10 by 10 gig clients. So we made a lag of 10 by 10 on the connecting to the Dell Z9000, the same 40 gig switch. And then we connected some of the servers. On the left side, you'll see this is the SDN demo that we had using the MPTCP, multipath TCP, where you can, if a server has multiple links available, for example, 4 individual links with varying bandwidths, for example, one link is at 1 gig, the other is at 5, the third is at 10 gig, then you can still transfer data without having a lag in parallel, without creating a congestion, just like a lag does sometimes when there's a single source, single destination. This architecture was just for the InfiniBand fabric that we deployed. It was kind of very complex with and took a lot of resources. Each object storage is one of the server node in the Supermicro box, all connected to the Mellanox IB switch. Then these are the clients facing on one side at 56 gig per second to the InfiniBand fabric, and 40 gig facing the WAN side, connecting to the same 4-stand switch and then onwards to the WAN. Okay, so this is when we started all these experiments during SC, and this is during the opening gala. This is all memory to memory. So during these tests, basically we start with memory to memory and then move towards the disk transfers while we keep optimizing our servers. This is a single box. I'll show later on a slide that explains just this path, where we had a single server with 2 40 gig NICs, and the box was able to handle 80 gig of traffic with just 5% CPU load. So you can see over here the University of Victoria, University of Michigan, and the Caltech, all with 3 colors. This is the Victoria, this is the Caltech, and this is the Michigan. So we had some troubles sending traffic to Starlight path going down to the University of Michigan because of it was still not clear that whether it was a dirty fiber. There was some packet drops in one of the switch, either within the internet too or in the Michigan. So we had hard time optimizing or finding the issues in that lane. And this was all using the FDT, the fast data transfer tool. It's a small Java transfer utility that is designed, developed at Caltech. Anyone can use it. It is freely available as an open source at fdt.cern.ch, and this is all TCP based. So this is the 100 gig storage transfers to University of Victoria with the FDT tool using the SSD storage servers, mounted SSD storage servers in Victoria with DDN InfiniBand fabric on the show floor. So we were moving traffic within this. So this basically this slide shows just the traffic between Victoria and our DDN storage appliance. And it is close to peaks of 90 gigs with sustained, you can say about like 75 to 80 gigs sustained. This is an overall picture that shows all the links, including the PATech, which I mentioned among the booths, Caltech, from Salt Lake City to Caltech, Michigan, and Victoria. So this is all in all. That shows a peak of 339 gigabit per second, 300 gigs sustained. And this clearly shows that if you have well-tuned server, then you're ready for terabit per second for supercomputing 2013 in Denver, Colorado this year. If there are links available, or if the vendors have the 400 gig which they are talking in the labs, if those are available. So we specifically thank to many of the R&D network providers, specifically Internet 2, for providing their 100 gig links, 3 unique 100 gig links, not just one, sharing with 3. And then we also acknowledge the support from Alcatel-Lucent, Ciena, Cisco, DataDirect, and all the other providers. So if you would like to design a similar system, then what should be the target features in such a box? It should be, it should have at least 40 gig E network port. It should be able to read and write from the same box at around 40 gig. And should use minimum CPU, and you should have software that can exploit all these features and the hardware capabilities. This slide shows a history of the 40 gig ENICs. As far as I know, Mellanox is the only vendor currently which provides 40 gig ENICs. So we started playing with their 40 gig NICs when they were Gen 2s on a PCI X8 slot. Then later on, they moved to Gen 3, which has higher traffic rate per lane, and it has a better encoding scheme. Otherwise, in Gen 2, in the Gen 2 PCI slot, you lose you have 20% overhead, and you lose about 20% of the traffic that you can go. And the last is their latest NICs, which can do either InfiniBand or it can do Ethernet, both on the same port. You just need to tune it via software, and it will work on the 56 on the InfiniBand side, or second port can be connect as a 40 gig Ethernet. So this is a kit that can be used to design a 40 gig E box. This is a Supermicro server. We like Supermicro because as mentioned earlier, you can customize very easily. You choose your own motherboards, you choose your own slots, you choose what kind of memory and processors sockets you need. So this is the CX3 Mellanox NIC, which can act, one port can act as an IV, or the other can act as the 40 gig E. We use the latest one, 9271 controllers from LSI. I mentioned specifically these active fiber cables because we had much trouble using the QSFP passive 40 gig cables. We see losses when the traffic goes beyond 30 gig. Either the cables are not to the specs, or the cards are not able to handle with the cables. So we use the new OCZ Vertex 4 SSD drives, the same 410 switch. As I mentioned, this was the first box that we had a chance to work on. And the server cost without the switch is about 15K. If you would like to know more about this, then I put some pages over here and you can take a look. So this is a plot using the 40 gig E NIC, and it shows that using just two streams, you can easily go to 33 or 34 gig of traffic. And if you have 3 streams of the same TCP and using the same FDT tool, you can easily saturate to the line rate maximum available to the card, which is 39 dot something. And the CPU utilization, you can see that it is well balanced over the 4 receive queues of the Mellanox. Mellanox has 16 receive queues. You can decrease them to 8 or 4 based on the cores you have available on the sockets. This plot shows disk to disk read and write among the two same servers. The disk write is about 30 gigabit per second. And this is a little old slide, but I thought that it might be interesting over here. That shows when we moved during supercomputing 2011 from 20 gig based old Gen 2 servers to the Gen 3 based NICs. You can see how much, you can see only 2 servers just provided the 30 gig per second of the WAN traffic. This is not a local data center or local LAN traffic. This is going to the University of Victoria, about 1200 kilometers. And you can see over here, that the Gen 2, the old generation, what they provided as a total of 40 gig traffic worth out of 2 boxes. So in total with 4 boxes at that time, we were able to go at 100 gig. And this was all FTT TCP. Now, if you would like to go beyond the 40 gig box, how you can make an 80 gig box. So this is another Supermicro chassis, which has 10 PCIe X8 slots. We used the Fusion-IO PCIe SSD cards, which are Gen 2, and same Mellanox, same force 10, same cables. These we used about either five. I think we used five of these duo cards, and we split them into half. You can split with the new firmware. You can split the drive into half, and can get more out of it. So we use about 128 gig of DDR3 memory. You need to have 2670 CPU with at least stepping level C2. C1 you will get problem with the PCIe slot and the generation 3. So this plot shows you a single server performance with traffic with the server receiving traffic coming from 2 servers from Pasadena during the show. So we had 3 servers in Pasadena and only 1 server for this 100 gig WAN link. This is based on the RFTP, RDMA FTP, which was designed by the Stony Brook and Dan Tong from BNL, from Brookhaven National Lab. So you can see when there was single server, and this is, by the way, all disk to disk. This is not memory involved. You are reading from memory from Caltech, but writing on the server, on the disks, on the Fusion-IO cards, on the show floor over the single 100 gig link. And you can see that it is almost saturated. So basically, the Fusion-IO were able to sustain more, or were able to get more right, but because of the 2 NICs, we were capped to 80 gig. And the CPU load, because of the RDMA, it was not using TCP sockets. There were no TCP continuous calls, so the CPU utilization was just 5%. Otherwise, if you would use some other application, then the CPU utilization will go about like 75 to at least 90% at this rate. So this is a little old slide, but explains how these new Sandy Bridge based motherboards and the architecture of those motherboards, and how now there's no PCI bridge, which is on the new in the new architecture. The lanes coming out from the Mellanox or from the LSI directly land onto the sockets itself. So there's no switch bottleneck that is on the motherboard, and there you can take the IRQs and map them specifically on the socket. So you know that I'm installing a card on this slide. Okay, that slot talks with the CPU socket 1, and then you can manage your traffic, and you don't need to put too much load for context moving in and out for the memory. Some of the hardware tunings that we recommend, if you would like to go at these levels, then Then you need to, so the Supermicro motherboard comes with default setting of Gen 2. You need to enable the Gen 3 in the slots. Disable the hyper-threading, otherwise there's more competition among the same core, different traffic coming on the same core. So you would basically go or map the only one process on one core to get the maximum out of that core. And then also change the PCI payload so you can get maximum PCI payload from the motherboard. Use the latest firmware. We have seen much issues with the old firmware. Of course, these days it's only latest firmware available. Use the QSFP active fiber. Don't use the QSFP passive thick copper cables. Dell 410 disable flow control needs to be enabled. Otherwise, the Mellanox will not go beyond 5-6 gigabit per second. You must have that enabled. In the switch that we had available, which is the 410, disable the 4Q and enable only the single Q model. And of course, we use the jumbo frames. Some of the software tuning part we use you can use either Red Hat Linux or you can use Scientific Linux or the CentOS, doesn't matter. You should be using at least the Linux version, the distribution after the version 6, because it has GCC optimizations. So you can recompile your code and get the optimizations from the GCC. So we use the FDT for writing on the, and you can have different model. If you would like to use the software rate, you can use the software rate. We have seen that the LSI in their previous firmware versions, if they are not up to date, then the RAID 0 basically has worse performance as compared to the software rate on the Linux, and software rate gives you much better performance. So use the kernel SMP affinity and bind the queues to the processor cores. Use the NUMA control so that the memory that you are using basically for that process, use that memory which is connected to that socket, and don't use the memory which is connected to the second socket, and then you are moving among the hyper transport among the processors. Change the kernel TCP parameters which are recommended, and there's a very good Mellanox tuning guide which is available on their website that helps optimizing the system and how you can get best out of tuning the Mellanox driver as well. Change the receive queues if you want to limit the queues to single processor. If you have, because then that helps moving the applications and LSI to the second socket. These are some other details. How you can change the for the LSI, how you can do the Mellanox, the way you can use the NUMA control, how you change the receive ring as well, so that sometime if the CPU is busy, the packet will still come in and stay for some microseconds into the memory of the card itself. So in summary, we can say that based on these experiments and the test results that we did during SC11 and SC12, we are almost ready for terabit transfers in SC13 if there's if the WAN links are available. The 40 and 100 gig network technology has shown the potential possibilities to transfer large-scale physics datasets. As we have seen that a single highly tuned server can now easily reach to 100 gig. In fact, we should have tried the 100 gig out of the same box that I showed you earlier, the 80 gig box. But due to so much work during the SC, we didn't have enough chance to try out the third card and try out that. And we have seen that during the SC12, the fast data application alone achieved an aggregate disk write of 106 gigabit per second over the multiple links using the SSD or the DDN InfiniBand architecture. And along with RDMA, RFTP, on a single box, we saw it going to 186 gigabit per second out of the same rack. We used Mona Lisa, and it very effectively monitored and recorded all those results at 40, 100, and at 339 gigabit per second, which was our maximum memory-to-memory results. That ends my slides, and if there are any questions, I'll be happy to take them.
Had several questions for you. One of your slides going to be online, or especially your tuning recommendations. Are they online at Caltech anywhere?
So they should be available on the on this link, supercomputing.caltech.edu/40gekit.html.
Okay, and then the other question was, what exactly was the problem you were seeing with the QSFP cables that made you go to active fiber? Were these the twin-ax QSFP cables, or what was the exact problem you were seeing?
So what I saw was frames getting discarded. If you keep monitoring the if config using the monitor and on the Linux, you can basically watch the if config every 2 seconds or every 1 second, and then you can see that the driver is dropping the packets. Now there could be many things. The first thing, when I opened a case with Mellanox, they said that use these specific Mellanox commands I can share with you later. Is there you can see if there's a problem with the cable itself, if the cable has some impedance problem, if it is not a right cable. I got some cable from Mellanox and some from Forsten. The problem with the Mellanox cables and Mellanox active fiber cables is that they don't work into the Forsten switch. It will be up, but the line protocol will not be up. Either they lock the port, or I don't know what's the problem with the Mellanox cables not going into the Forsten. So if you have Forsten cables, they work fine with the Mellanox NICs, and they work fine with the Forsten switch as well. And they work fine with, for example, Juniper or Alcatel. So they told me that use these Mellanox specific controller debug applications, and then they showed me that it's your cable problem. As soon as I switched the QSFP copper cable with the QSFP active fiber cable, all the errors were gone. And sometimes it happens. Another thought is happens when the cable is not properly latched into the card as well. If it is not properly inserted, you'll see errors. So and in the previous firmware and the drivers I have also seen, if you pull out the cable a couple of times, the driver will just hang, and you have to restart sometimes the whole box.
Okay. Thank you very much.
Yes. So we had some problems with how the hashing was done on the Juniper. It was not balancing the traffic properly on the Juniper. The 100 gig part was okay, but the way it was balancing over the lag, because we had 100 gig link going out to Victoria, we built we designed the WAN in a way that we have a redundant 100 gig switch, so that there are 300 gig links. If one of the switch will be broken, then we should have a backup path. So we terminated one of the 100 gig on the Juniper, and then the 4 10 gigs were going to the Forsten switch, so that we could connect the other servers to the Forsten and then make a lag and send the traffic out on the WAN. So the lag was not behaving well, and it was oscillating too much. We didn't have issues on the Alcatel or the Forsten. Okay, thank you very much for your time.
Thank you, Azher. So any other final thoughts, questions for our presenters out there? Mark, I did have a question for you, and do you have any recommendations for communities like San Mateo? I mean, you said that there are other communities asking, you know, how can we get this type of partnerships going, and what would you recommend to communities so that they can outreach to partners? Because it seems like it's a win-win situation, right?
Yeah, I think it's up to the communities to get their business leaders, their property owners, the Chamber of Commerce, and the City Council. If the property owners will work with a cable company or an MSO to provide access to their clients, if the City Council makes it easy in terms of getting the permitting, because one of the things that really slows down building in communities, and especially in metropolitan areas, is just permitting, and just kind of the policies of the City Council. Because there's a lot of cable companies and carriers that would certainly like to provide these communities with fiber, and sometimes it's just simply political. So the community has to kind of upstream get those things kind of handled internally, right? It's kind of handled within the family before they go out and approach either CLECs or carriers or cable companies to make this what is usually a multi-million-dollar investment, even for a small city like San Mateo. So I think that's kind of the kind of upfront requirement for them to be successful.
Thank you, Mark. Any insight? I know that in our communities we have challenges with Indian reservations. Have you had any challenges there?
No, we haven't had challenges there. The communities that are approaching us at this point, it's interesting. They're all up and down the peninsula, those small cities. If you go up and down El Camino Real, right? It's interesting that the Silicon Valley, there's so much technology coming out of it. You've got the venture hub of the world, but there's still a lot of small communities that are right next to the venture hub of the world that really don't have broadband capacity. So there was a couple of small businesses that became very big businesses that had to move out of San Mateo. There were software companies that had to move out of San Mateo just for this reason. And as you know, I mean, the cities are looking for these tax dollars also. So this is going to be very interesting to see over the next 4 or 5 years. And I was just very glad to be part of at least the first one in the cable industry, the San Mateo piece.
Thank you, Mark. So if there are no other questions, why don't we give a final round of applause to our presenters?